All right. Thank you, Liang. And good afternoon, everybody. It's very kind for the department to invite me for this colloquium talk. Yeah. So as as Dr. Cohn just mentioned, I joined Loyola Chicago a bit over a year ago. Before that, I spent my graduate years in Alabama, Virginia, and then I did various postdocs. So this talk, the topic in the talk today, started actually during my first year of postdoc at Wayne State in Michigan. But then just like every other projects, when you're trying to attack some new problem, you need to gather various tools, which some of which you may know, some of which you may not, and then you have to learn for them. So I hope that hopefully, as I can see, many of the audience today are students. I would assume that we have some undergrad audience here, right? Like I think that's what Liang was telling me. So hopefully my talk. So my intention is that at least the first half of the talk will be somewhat relating to hopefully the courses you've been taking or will be taking. So in that regard, please feel free to ask questions at any point of the talk. Be like, oh, is this the same thing, or is that related to the other course I want to take? I'm happy to sort of connect the dots for you. And then I also want to use this talk to showcase like really what is happening for math research. So without further ado, I assume you guys can all see the slides. So the title of the talk is the two-dimensional Laplace equations with line fracture, and will be both a qualitative and quantitative analysis. I particularly like this piece of work because it, to me, is a very good chance to combine these two part of things that I learned over the years, which at some point seems somewhat, distanced, but I was able to join them together in this publication. I have to mention this was a joint work with three of my colleagues, Hengguang Li, who is the chair of the math department at Wayne State, Peibong Ying at the time. He joined later of the project as a new postdoc at Wayne State, and now he's a recent tenure track faculty at University of Texas, El Paso. And Lewei Zhao at the time was a postdoc, and he's now a resident at Stanford University. So I want to start. So here's the outline of the talk. I will introduce you to the problem itself. And indeed, this problem with this 2D Laplace equation is something you can find in the first 20 pages of almost every PDE book. I'm actually teaching the PDE class right now at Loyola for the undergrads and some grad students. So we mentioned this in the first day probably. So as you can see from the quantitative, which means, from the analysis or so-called analytic point of view, is a well-solved problem. But the challenge or the new questions we're facing comes from the second part, which is the numerical approximation, because we need to approximate this systems to produce results that can be used for, should that be industry, should that be physics or engineering, and et cetera, et cetera. New questions arise. And then, which give us the motivation to actually go back to the theory and then to explore, let's just say, alternative answers to the question we already answered, but this time hoping to answer the new questions. All right. So hopefully this is what I can convince you at the end of this hour. So so here is a setup. So I need to set up the math question. So this is so-called differential equation. So the equation we're considering happens on this general geometry of interest, where I'm considering a bounded domain in R2, which means is a plane. Of course, the problem has their own counterparts in R3, which is physical, or it could be high dimensional for mathematical reasons. The domain, so this is the second part, I should probably make this full screen. I just realized, yes, this is probably better. The boundary of the domain, omega, is smooth. So this Cn+1 means the boundary is n+1 times smooth. And then we consider this domain has a fracture. So in the middle, there's a line segment. This segment is considered to be well contained inside my domain. So in other words, it's not touching the boundary, which is critical. This problem has also its extension where you can consider this domain and you sort of like just cut it in half, right, in the middle. That will be a completely different situation. So a fracture is denoted by gamma. And for simplicity, let's just say that gamma is the line segment from 0 to 1. All right, this happens quite a lot in applications. I'm just putting 2 examples up here, and particularly for the Laplace equation. First is the so-called Darcy's law or Darcy's flow, which happens a lot in the porous domains, where this is, I believe, a piece of either wood or stone, probably stone, where you have this thin planar structures where, say, water, like rainwater, can just flow through. And we need to understand how the dynamics there goes, where the Laplace equation naturally arises. And the second is the more understood heat transfer. So if I have a domain and I have the heat flowing around it, it's a 2D domain, where in the middle of this domain, I have this structure, or this so-called singularity structure. And I would like to know what is the steady state, which is what happens in the long term when time goes to infinity. So for large time, what is the final heat or temperature distribution would be like on this domain? And so this is all very common questions people ask. Now, so Laplace equation itself, the Laplace equation is formulated as negative Laplacian of this function u. So again, it's a 2D domain. So u stands for often the quantity of interest, such as temperature, such as displacement, and etc. So the Laplacian of u, and hopefully for those of you who is or had taken multivariable calculus, you recognize this symbol. Laplace means partial derivative to all the dimensions twice, so second order. So this is, in this case, is u xx plus uyy. Now, here is, in case any of you actually knew Laplace equation, you may actually raise a question. Well, this is not really a Laplace equation, because Laplace equation goes as negative Laplacian u equals 0. When you have a non-zero right-hand side, which I'm writing here as this delta function, it's called Poisson equation. So this is, long studied problems. So we call it still a Laplace equation, really following the literature, even though this is indeed a Poisson equation. Well, at the end, the name doesn't really matter. Our right-hand side is this so-called Dirac delta function. This is probably not covered in most of our calculus class because it's not a function. Actually, if you see what what I'm writing here as a definition, you must oppose to it, because it is a function defined as such that equals infinity. In this gamma, we know no function can be defined as infinity, right? And equals 0 elsewhere. And then most importantly is that the integral, or by the way, this integral is a double integral, because this omega is a subset in the R2, right? So I guess I'm writing just as one single integral sign in a common practice. So this double integral of this function actually equals 1. So in other words, this function, or mathematically is actually called tempered distribution, represent this very physical phenomenon where all your mass, which is 1, is concentrated on just a single side, right? Which is this gamma. Therefore, I guess one line out of a 2-dimensional domain has 0 area. So on this 0 area region, it accumulates infinite much height, which make the integral equals 0. So physicists use this all the time. We need some more advanced theory to study them. But let me just state really the idea, okay? So infinity at this line, 0, so you have a huge jump, so to speak.
Yeah, Dr. Wan, can
Yes.
I ask a question?
Oh,
So,
absolutely.
Yeah, the gamma looks like the measure of the gamma is 0, right? Is that just
absolutely,
like
absolutely.
just a segment? Okay.
Yes, absolutely. So the standard Dirac delta function is in 1D, where you're only infinity on a single point and 0
Right.
else. So it's the same situation, but extended to the 2D case.
Right. Yeah, intuitively, so the integration is equal to 1. It's hard. Intuitively, it's hard to understand,
Yeah,
right?
which is
Yeah.
actually I was in my PD class. I have a lot of physics students. They all learn about this actually in their first year physics class. Physicists use these functions back in the mid 19th century,
Okay.
eventually, without a math theory behind at all. But they're just like because they really need. I mean, what is it? This is really particles. The particles are taking zero space, yet they're concentrating all the energy. So they need these delta functions to represent them. So I think the math theory behind them eventually come around at the beginning of the 20th century, some 40 years later. So it's now well understood.
Okay. Thank you.
So this is the like the mass of 1 that's distributed on a measure of 0, like on the
Correct.
area of 0. So
Correct.
that's why we got the infinity. Then on a higher dimension, it would be so I'm just imagining that the fracture on a higher dimension would be a plane that would have 0 volume. So it would have something defined similar like
or a
this.
line, right? Actually, this is a very good question. At the end, you will see we do ask the similar question of this talk happening in 3D, where your fracture could be either a surface, which the simplest is a plane, or also a line, right? Because on a 3D, both the line and surface has measure 0. And then guess what? The answer will be completely different. That's also like interesting phenomenon happening here. Anyway, so for the students who did not learn this before, all really what we're really seeing here is that there's a weird function where it takes infinity at this line, 0 elsewhere. So it's huge jump. This actually will have quite an application in the next slide, because even though you did not take PDE, right, as long as you understand what derivative is, which is what we talk about in Calc 1, you will see an issue. The issue is the following. This Laplacian is second order derivative. So on the left-hand side, I have second order derivative of a function u, which naturally needs to be twice differentiable. There is a big theorem from calculus or analysis saying that if a function is differentiable, its derivative actually cannot be just some arbitrary function. In particular, its derivative cannot have jumps. I don't know if any of you have taken this, but if you just think about any derivative functions out there and their derivative, the derivative cannot jump. But guess what? In this model, I am equaling it with a function not only have a jump, it has a huge jump. The jump is infinity, and also back to 0. So I have a huge jump. So this equation, in another word, makes no sense in a classic way. There's definitely no function that is second time differentiable that would satisfy this PD period, right? So in other words, it has no solution as a classic function. So we have to search elsewhere, right? Because this thing does happen in the nature, and we do want to understand them. So this actually leads us to consider the so-called weak solution. So the classic solution or the strong solution cannot exist. We have to go to something secondary. The weak solution, which a classic solution is only considered by its differentiability, in this case twice differentiable, but now we need to weaken it, which really means that we will weaken the differentiability but ask a bit in its integrability, right? So this is sort of the trade-off, and I want to give a quick introduction to you guys, even though this may not be covered, but it sort of represents a good idea in how we treat these things in math. So again, Cn functions are those that are n times continuously differentiable functions. So I have a few examples in this slide and the next slides, and they're often covered in your Math for 16, which I believe is a real analysis class. So for those of you who have not taken that class, please do. It's fascinating topics over there. So we can talk about functions that is just continuous but not differentiable. I'm actually putting an example here. This function which is defined as x times sine 1 over x everywhere, but obviously that's not well defined for 0. So at 0, I'm just defining that to be 0. This function is clearly continuous, right? Everything just ping, going toward the 0, but it's not differentiable. You probably can feel it's not different because I have so many zigzags and they're actually happening. This oscillation is happening so frequent that the derivative, or say the limit of the rate of change, right, from Calc 1 is changing so rapidly. There's no limit happening. You can twist this example. You can twist this example. So this time it is differentiable. So now if I'm squaring the x squared, so my function is still doing this fast oscillation, but not with that much amplitude. This function is continuous and it's actually differentiable. You can't use calculus just though. You have to use the thing from real analysis to prove it, but its derivative itself is not differentiable. So it's only one-time differentiable. And you can keep going and construct particular functions of exactly n times continuously differentiable. And then the argument will be by a math induction. Okay, so this is differentiability. Now, I told you the weak solution asks something from differentiability, but also something from the integrability. So this is what we meant, right? This is the Riemann sum that you learned at the end of Calc 1 about whether or not a function is integrable. We call this the LP space or the LP functions, which is the function that is p time or pth power integrable. And by which what we meant is that the integral of the pth power of the f value of f is finite. Shall this be the case, we call this pth power integrable. I mean, we consider only for the cases where p is greater or equal to 1. You don't talk about p less than 1 because it's not a, we call it, it's not a norm anymore, it's a semi-norm. But anyway, examples, right? This 1 over x, which you may remember, if you take the integral of 1 over x from 0 to infinity, it diverges. Actually, it diverges both at the tail and at the head. But for any p greater than 1, it is convergent, it is finite. So 1 over x is in LP. If you consider just the finite interval from 0 to 1, this 1 over root x is also a LP space for between 1 included and 2, so strictly less than 2. So these are all something we can actually write down using the improper integrals, using the limit techniques from, I believe, in Calc 2. All right, so we talk about integrability as well. Now we put this together, and there's a special case, which is when p equals 2. When p equals 2, so this so-called L2 space has an extra special structure. There is an inner product on it. And by that, what we meant is that if you define this f inner g, so the inner product between f and g, to be the integral of f times g, then this thing, so-called inner product, satisfies these three nice properties. There's symmetry, there's linearity, and there's positive definiteness, which means that when f dot, so if f inner f is 0, that just means f is 0 for continuous f, of course. This is exactly analogous to the dot product you guys learned in the beginning of your vector geometry in multivariable calculus, where you have vectors, dot vectors. This is extending that idea to functions. Now, one good thing about it is that, if you recall, the dot product gives us the geometry, right? If you have two vectors and you're allowed to do the dot product between them, you can find the angle. Like we have this formula, right? V dot W is V norm dot times W norm times what? Cosine, right? So we actually can find the angle. Same thing for functions. So amazingly, you can start to talk about geometry of functions. And this is really, so this is what the inner product will give to us. And then you will see soon in the next slides why that matters, right? So we can talk about angles, we can have a length of a function, we can talk about the projection of one function to the other, and etc., etc., etc. So we can talk about space with geometry for functions. So this was Hilbert space was named after the celebrated mathematician David Hilbert, which you may know, right? He was, there's all this 23 Hilbert problems and etc. that he brought up in the ICM conference in 1900s. So this is a picture of him. All right, now back to what we need. Remember, we are on the task of defining this so-called weak solutions. All right, so I'm now combining the differentiabilities and the integrabilities, and this was done in the 30s by the Russian mathematician Sobolev. So we have this space so-called WNP. At the end of the day, it's not critical to remember the symbols. What you need to see is these two indices as superscript. M stands for the differentiability, weakly though. P stands for integrability. So basically, a WNP function means a function that is m times differentiable, whatever weakly differentiable means, right? Differentiable, and p power integrable. And just like before, when the p equals 2 is a special structure is a helper space, so we denote that by HM. All our following discussion will be happening on HM spaces. So we do need the geometry. All right, so back to the story. So recall this problem I'm considering has no classic solution. For that reason, I'm now going to reformulate it. In particular, we call this a weak formulation. And this is really just a, integration by parts. So what we do is we multiply this equation, the first line equation, by a testing function v. This v is exactly in this H1 space. It has a subscript 0 because I need the boundary to vanish, because from integration by parts, I want the boundary term to be gone. And then I can shift one time of differentiability to the v. So in this line of weak formulation, as you can see, things start to be different from before. I'm no longer asking my u, this unknown function that I'm trying to solve, to be twice differentiable anymore. Unlike the original problem, where I have Laplacian. Now I have the gradient. Gradient is just partial derivative. So I only need u to be one time differentiable. So I gain that. Well, what do I have to pay? Well, I have to pay the price that now I need to ask u to be, integrable. So in particular, u has to be in this W12 space. It's one time differentiable, second power integrable. So this is what we call a weak solution of the problem. All right. Is there any questions so far? Okay, hopefully that's.
I have questions.
Yes, absolutely.
So what exactly is the difference between like a weak differentiability or like a weak integrability?
Right.
Okay.
So
or like compared to the normal one.
Absolutely. So the regular differentiability is just, so when, in Calc 1, we say, when we define a f derivative, right? Like what is f derivative? You just take the limit of the difference quotient, right? F of x plus h minus fx divided by h, send that h to 0. So that's the classic or strong differentiability. The weak derivative is actually defined. So this is actually the definition. So, oops, sorry. This is the definition. So the weak derivative is actually defined by the integral. So the weak derivative is saying, well, if the inner product between the weak derivative with all the other testing function v, right, act just like the derivative, then you are the derivative. So the weak derivative is defined by this integral and through the integration by parts. Because remember, what does integration by parts do? Integration by parts shift the derivative from one function to the other, right? Like integral u dv is eventually equal to something about integral v du, right? So you shift the derivative of v to the derivative of u. So that's sort of the idea. So my function.
I don't know. I didn't really get it.
Sorry?
No, I didn't really get it. So kind of confused. Sorry.
So yeah. So okay. So look at this weak formulation, right? If you compare the two sides, on the left hand side, I have this, I have this gradient v, and on the right hand side, I have this v, right? So what happened to that gradient? Well, that gradient moved to the other side, right? So gradient of gradient is just Laplacian. That's how with a negative sign, that's how we get the negative Laplacian, right? So in this case, if this is true for, the key point is for any v. So this is saying if this holds for any good testing function from my H1 space, then I'm just regarding these two things as the same. Then I'm just saying that's my derivative. That's sort of the idea about the weak derivative. So of course, if a function is smooth enough, then its weak derivative is just the same as its standard derivative, right? So if you're asking me what is the weak derivative of x squared, well, the answer is 2x because it's just the derivative, right? But the problem is if the function is not differentiable, then you cannot talk about its standard derivative, but you can still talk about its weak derivative through integrals.
So Rudy asked in the chat. Sorry, so Rudy asked in the chat, he says, so weak is stating a derivative should happen, implied versus showing the derivative.
Should happen, implied versus wait. So weak is stating a derivative should happen, versus showing the derivative. I think a more accurate way is to say that instead of say should happen, is that weak derivative admits more function to have derivatives, right? Like if a function has, as we know, if a function has a whole, then it's not differentiable at that whole, as we all know, in the classic sense. But such situation will be differentiable in the weak sense. I'm not trying to say any function are weak derivative, weak differentiable, of course, but weak derivative allows much more functions to be differentiable.
Oh. So is it like the case that like, you can't really like fully differentiate the function, right? Like there's a whole somewhere, but like that like if you're like everywhere else, like that's not the whole, that like it still works as a normal function in a
Exactly.
sense.
Right.
Okay.
In that sense, yes. And then
Okay.
mathematically, how do you justify that? You justify that by integrability.
Right.
Right. You pay the price, so to speak, through the integrability. So yeah. Right. I'm glad these questions are asked. Yeah, these are very important questions to understand sort of the fundamental idea behind. And surprisingly, everything that involves the modern research about differential equations, which naturally derivatives appears, are going to go into the weak sense because classic derivatives is just too much to ask. Any other before I move on? Okay. Let me shrink this a little bit. All right. So next, I'm gonna go to the second part of the talk. I'm gonna switch gear a little bit. We will come back. So next is actually, I think I skipped a few lines. Oh yeah, here of course I forgot to mention about the theorem. So this is all theory back to I think this was known to my background at least in the 40s and 50s. We already understood this pretty well. This Laplace equation has a weak solution, and the weak solution is unique actually in this space. We even know the optimal space that the weak solution exists. So we know the short result in this h3 minus epsilon. Again, all that means is that it's 1.5 minus epsilon times differential, or whatever that means. It's not critical, but that's the short result that we already know before. So this is
Wait,
yes,
I have a question, sorry for
absolutely.
interrupting. Is that the case that like it's a formula that you use to get like an integer amount of differentiability?
Right.
Or
So
is it
far,
like okay, I was gonna ask if like you could like somehow do a half differentiable
yeah,
somehow.
naturally, right? Naturally. So of course it does raise the issue, like what do we mean by saying half differentiable, or say in my case, what does it mean to say 1.49 times differentiable, right? It's no longer clear in the classic sense. But so my short answer is that yes, we first establish the integer case, right? 2 times, 3 times. Then we talk about the negative ones. We have to talk about what is -1 times, which is done by this thing called do space, which is exactly those inner products are doing. Because when you do the inner product, there you're pairing things up. If on the left you have 2 times, on the right you can see that as -2. Okay, so you have positive and negative. Then you do this thing called interpolation, meaning that you have ways from the pure math. By the way, this is another place where the pure math comes in, right? They allows us to interpolation, meaning that you're finding the balance point between the two. So if you have a 1 and you have you have a h1, you have h2, and you play different weights, then you can get the things in between. That's sort of the rough idea.
So like so I don't fully understand, but basically it's like you can, so if you know like that there's like the regular function, then you have like the first differentiation, you can sort of interpolate between them in some way.
Right. That's sort of that.
Interesting.
Yeah, that's sort of that. Exactly. Okay. So all right. So yes, as I was saying, we're gonna temporarily leave that and then talk about the problem we're actually facing. So we're trying to work on sort of simulate or numerically study that Laplace equation numerically. The so-called finite element method is one of the most widely used method in numerics. They have a lot of advantages. So here's the rough idea. The finite element is basically to say, well, you are studying an equation on some domain. So I first do a triangulation, what we call a meshing. We do a meshing on a domain, and then you have to, on this meshing, So once you do a meshing, as you see in this picture, you have a lot of nodes, which is the vertices of these triangles. Then your calculation is only going to happen on those nodes, right? So this is called scheme. You put your PDE, you rewrite your equation into a discrete case on those nodes, and then you start to calculate them by iteration. So you give an initial value, you do one-time approximation, and then you do another refinement, which is the second time. So the more you go, the more accurate your approximation will be to the actual solution. So that's the rough idea. This is sort of the rough idea for almost every type method of calculation, but specifically for finite element, because they use the triangulation meshing. All problems mostly come from this. And here I'm just showing you other pictures. This is all classic cases. Actually, the first one is the standard triangulation of the disk. The second one is on I guess, a quarter of a ring. Here we have a standard elasticity problem, right? Which you have a beam, and it was having some sort of a deformation. And then the last picture is how it was used in the industrial case. Right? So almost all the subject, all the geometry can be well approximated by this triangulation meshing. So our problem, we're making a very abstract mathematical simplification. I have on my domain in R2, which I'm now just saying, oh, let's just consider a a square. My line fracture, if you recall, is that gamma is just a line segment between, I think I said to be 1/4 to 3/4, sitting in the middle, sitting in the center of my domain. And then, then you say, well, how am I supposed to do this triangulation? The first thought is, of course, to do a uniform one, which means that all my triangulation are of the same size. Now, naturally, if you want your calculation or your approximation to be more accurate, then clearly you should do more triangulations. So this is just, you should refine also your mesh. So on the second picture is the first time of meshing, and then the third picture is to do one more round of meshing. And you can, of course, go on. In case you wonder, why can't I just do this forever? Well, the more you mesh, the more nodes you generate, right? The more triangles, the more vertices, the more expensive your calculation is. And then it's more costly, and then, either time-wise or resource-wise is going to be impractical. So we actually did the calculation, right? I'm going to skip all the details but this is basically what you can find. And then the color, the legend of the color just tells you the value of the U. So we have zero boundary condition, meaning that the U is always 0 on the 4 sides of the large square. And then in the middle, the value is gradually, raise up in the middle. Okay, so this is something one can do, if you do a one semester thorough study of finite element. It's quite well understood. What's the issue though? Right, we're facing an issue. The issue is we will ask, is this meshing optimal? As I mentioned, if we want to get better approximation, we shall keep mesh, right? We'll keep refining our mesh and keep refining our iterations, but then you have to do a calculation on, like, am I doing an optimal approach before I invested a lot of resource and time into this? Right? Of course, this is just really a baby problem, but representing all the really applied problems sitting behind in concrete field. So let's do a quick demonstration. I hope that most students here can actually see. So 2D maybe is too much to see. Let's actually do a 1D. In the 1D case, the Dirac delta function is just really a point mask on the middle point of this interval 0 to 1. So it's just at 1/2. I have this 1/2, which the function equals infinity, elsewhere it equals 0. The Laplacian now just becomes second order derivative. My boundary conditions just become 0 on the two ends of my endpoints. So maybe some of the audience have taken or are taking the differential equation class, and you actually will see this. This is a second order constant coefficient ODE. And of course, like before, the calculation, the approximation is only down on the nodes, right? So I'm now separating, I'm mashing this line segment of length 1 into 12 pieces versus 13 pieces. Therefore, I'm generating all the internal nodes of either 11 or 12. I'm only doing my calculations on them. And this is what I got. On the left, I had 12 nodes and on the right, I have 13 nodes. Now, and in each of this pair of pictures, on the left is just a numerical approximation, which is kind of reflecting what you saw here. On the boundary 0, and when you're going toward the middle, the value raise up, right? So it's exactly like this. On the right, you see the arrow. Because for this ODE, we can actually solve it explicitly. We actually know the true solution, so we can easily just compute the arrow. So here are 2 arrow page. I hope you can see it clear on your screen of the number. Some of the numbers are pretty small. I apologize for that. But if you compare those 2 pairs closely, you may make some interesting observations. Number one, the one on the left is, so the one on the left, this triangle, is actually the true solution. The one on the right has this, vertices chopped off, like it's just approximated by a straight line. But more importantly is about the arrow. On the left, my arrow is about 1.2 times 10 to the negative 16. That's 0 with, that's 0 with 15 other zeros and a 1. On the right, my arrow is about 0.04. I mean, they're all done after the same number of iterations, of course, just to have a comparison. So in another word, both arrows are relatively small, but the arrow on the right is really 10 to the 14 times of the left. That's a huge amount of difference in the arrow. So what caused them? The only difference is the number of nodes, or if I show you this picture one more time, right, is 12 versus 13, not that much different. But the critical thing is that this singularity at 1/2 on my left picture happened to be one of my node, where on the right-hand side is in the middle of 2 nodes, which means I'm not doing calculation on it, right? Remember, the calculation is only down on the node, not in the white space in between. So singularity on the nodes versus singularity not on the node. The former one is reducing much less error than the later one. That's the observation we get from the 1D case, right? And also, when the error is happening, it is actually happening at the singularity, which is the third picture you were seeing, right? Like this arrow actually happened on this chopped off vertices of my numerical solution. So because of these observations, actually the same thing, later on we understood the same thing was observed also for the high dimension, like 2D, 3D calculations. So this tells us that those singularities where you need to pay more attention. In particular, when you do your matching, you need to make sure that your nodes are always landed on those singularities, and you probably need to do more approximation around them, because that's where the errors are happening. All right, so this is the so-called graded mesh. In the case of uniform mesh, which I showed you earlier, you always refine your mesh by the same size of triangle, the same size of triangles. What you do is, so on the top 2 pictures, I start with 1 triangle, and how do I get the second triangle? I just pick the middle point of each side and connect them. So 1 triangle becomes 4 triangles, and I just keep going. So every time the number of triangles just multiplied by 4, and then I have also extra vertices. Whereas now in the second row, if my x0 is one of those singularities, then I want to do a so-called graded mesh around them, which means that when I do the mesh, I'm not going to pick the middle point. I'm actually going to pick the point a bit closer to it. So my grid are finer around the singularities, and elsewhere it doesn't matter because that's not where the arrow is emanating from. And so that's the simple idea about graded mesh. And this is a more mathematical framework about it. So what we do is, if Q1 is a singularity, then I pick a refinement parameter kappa, because I'm making these triangles similar, right? So this kappa is the ratio between this L1 versus L2. Of course, if that number equals 1/2, you have a uniform grade because you're picking middle point, right? So this is simply just the framework about how I do the so-called comma refinement, right? So I hope the idea is somewhat easy to follow through these pictures.
Dr. Wan.
Yes.
I think Yifei has a question.
Absolutely, yeah, please.
I need to unmute myself. Sorry to interrupt. So I wanted to make sure the singularities here, does it mean the places where it's not differentiable in the normal sense? Is like the
The
so
singularity
is
here,
this
the singularity means the fracture in our
fracture? Okay.
Right, exactly. Yeah,
Yeah.
those are the fractures.
Okay.
Yes.
Thank you.
Actually, you know what? I do also want to add that. Well, so I guess I give you part of the answer. I said that because our problem was actually to study the effect of the internal fracture, right? So I believe one of the students or I forgot whoever asked, if I have singularity on the say boundary, well, yes, those also need graded the graded mesh, absolutely. Of course, our conclusion now find out that the boundary, like, so I have a corners, right? The corners on the boundary is also like, instead of a circle, if I have a square, then those four corners are clearly also creating some sort of singularities. The roles they play to the whole problem are different, internal versus boundary. At the end of the day, you do have to consider everything. This talk, however, only focus on the interior case.
Okay.
Yeah.
Thank you.
Absolutely. So here is just a quick demo of how that is done. I start with this line. Oh, actually, yeah, here's the answer to your question. So I start with this line fragment internally, and then I first do one round of uniform mesh, right? But as I'm doing my refinement, I do the kappa refinement, where this colored line or every triangle that is connected to it got a graded. Actually, is this two endpoint? And I will talk about that why. That is connected to those, all the triangles connected to those two endpoints got an extra graded mesh. Everywhere else is still uniform. And then so forth. Right. So at the end of the day, around those 2 points, you just get very, very small triangles so that you can do your calculation on those nodes, which make the arrow, which you know, supposed to reduce the arrow. Elsewhere, it's uniform. So we actually did this calculation. We do get somewhat better result. Okay. And here's one thing we observed from the result. So there's a lot of numbers. And let me explain what they are. So, I mean, Laplace equation, actually, we can also solve it analytically. So we sort of like know, but here the first line, we're computing the so-called relative error. So, you know, the superscript n and n minus 1, n plus 1 just means the number of iterations. So this is saying that I'm computing the ratio of the previous iteration and the next iteration, like how much I improve, so to speak, right? How much is this improving? Ideally, this will go to 1. Right? I'm also taking a log. So ideally, I would like this to go to 1. All right. So what is happening? If you see the table below, you see that on the vertical column, I have different kappa value. Right. The smaller the kappa is, if you remember the picture, the smaller the kappa is, that means my graded mesh is more going to go toward the singularity. If kappa equals 0.5, it's just the uniform. Okay, so we did all the experiments in between, hoping to find the optimal way. I mean, maybe the first thought is, well, of course I should do as small as possible. A smaller refinement, the smaller I'm approximating my singularity. But that's really not the case. We're showing by this experiment. As you can see, at the uniform meshing, right, like my arrow rate, this E is like 0.8, 0.8, 0.9, 0.9. When my kappa becomes a bit smaller, the performance gets a bit better. Yet, if it keep decreasing, it actually gets worse, right? So if you compare all those numbers, you probably can find yourself where the best performance is at. Of course, we only did like, you know, a few discrete values. So the best performance happens somewhere between 0.15 and 0.25. Actually, on this table, the best one is 0.2, but you know, maybe 1.21 is better. I don't know. We didn't do that. So it's somewhere in between, around 0.5, we're having the best performance. This is actually what really caused our interest into study this problem. Quite anti-intuition. This can be also done on the non-symmetric convex domain. So if not a square, right? So the symmetry is not really playing a role here. You do the same thing, right? So your refinement is around the endpoint, and you have the same. We have the same sort of findings. The best performance is around 0.2, let's just say between 0.15 and 0.25. And we would like to know why, and we would like to know how. I mean, you can of course do a lot of experiments, but the best thing is you can do is of course to get a theoretical result, and then know that before you even do the experiment, because maybe each of this is very expensive, right? You would like to know where is the optimal kappa you should choose. Okay. All right. I should watch out the time a little bit. But I think I'm actually giving the idea, hopefully. So this is our second question. What is the value? What is the optimum value of a kappa, right, for us to obtain the optimal convergence rate? Therefore, we can construct the most efficient, also the cheapest refinement framework. And here is exactly the obstacles that the question that is already answered, that in my first part of my talk, some 70, 80 years ago, that U is in this space provides no help at all. It tells us theoretically where the solution exists, didn't really give us any insight about the numerical considerations. And this is a reason why we need to go back and revisit the problem. So I do want to speed up a little bit on my third part, because this now involves, a lot of the rather more modern literature. So this phenomenon was first observed. Well, one of the first observation of this phenomenon was in '84. Walbing was a famous mathematician in Cornell, and I think there's some chat. Oh yeah. He was a famous, mathematician in computational mathematics in Cornell. And I think a lot of, if you check the math genealogy, a lot of the modern people are sort of the offsprings from his root. Griswold and Dodge, they are the one who studied this heavily on the elliptic problem, which is exactly what these Laplace problems are, on non-smooth domain. So both are, famous people back then in France. I should say this problem was heavily studied in Europe, and more recently calling attention in the US. Jerison and Koenig actually brought this Lipschitz domain conditions in 1995. Jerison, I think now is so Koenig is this famous Argentina professor at University of Chicago. We actually talked about him because I believe October is the Hispanic Heritage Month. So we were actually talking about, famous Hispanic mathematicians. And turns out Chicago has a cluster of Argentinian, including the Capobrari, who just got a Nobel Prize this year, which you might have heard. Jerison at the time was a postdoc of Koenig at Chicago, who is now, I believe, a professor at MIT. And then Mazzucato and Nistor, I think Nistor just retired. They are, very famous mathematicians in computational math in Penn State. So Penn State has a lot of people, including one of my collaborators, were from that. So they also studied the general polyhedral domains of the similar problems. All right. Actually, a lot of our results, the ideas comes from some of their early work. So I want to, I know, okay, 150. So let me actually just jump into this a little bit and just give you overall overview. So classic Sobolev space does not really offer the answer. So, however, in the literature, this was done in 1959. This Russian mathematician, they defined this so-called inhomogeneous weighted Sobolev space. So, without going into the detail of the definition of this Sobolev space, on the top of differentiability and integrability, they also add the weight. What are the weights for? The weights, you can think of it exactly, connected with the grades, the kappa refinement we're talking about. That's exactly the weight. So with this space, we actually were allowed to study this problem a little more detailedly. As you can see in the picture, instead of answering the question once and for all for the whole domain, we actually have to decompose this domain into 1, 2, 3, 4, 5 parts. You have the two smaller circles or disks around the endpoints. You have this omega plus and omega minus, which is attaching part of the fracture away from the domain, away from the endpoints, and then you have the rest of the white space, which is like behaving supposed to be nice. Okay, and with this weighted Sobolev space, one actually can have a precise description of the solution. So, so this remark, everything I'm writing here is a more detailed result from that H3 halves minus epsilon result. So we now know exactly on which weighted space they're in, depending on which location they're in our domain. So so this is the main result where we started our research. This is by Li, which is who is one of the co-author of the paper, Mazzucato and Nistro from 2010, which basically have an estimate, right? They estimate the error between the true solution and the approximate solution near the endpoint of the singular line. Right? So this really gives a framework, and this is explicit. As you can see, this kappa is actually equals to this quantity, right? Which is 2 to the negative m over a, where the m is the differentiability, or +1, a is the integrability. So this perfectly connects the two sides of the rim. The theoretical regularity, so all this m and a, perfectly answers the question in the numerical side, which is what is the optimal refinement parameter kappa, right? So so now the question we're really asking is, what is the case for us? We have this framework. We now know how to answer the question. So the thing for us to do is to find that m and find that a for our problem, and that's what we did. So this is the paper. The first draft was finally published in 2021. We were preparing a following work. We answered the question completely. 3 parts: interior, or close to the endpoints, or close to the boundary. Right? Again, the detail doesn't really matter. All I want to really say is that is why we need to decompose the domain. We decompose the domain because the answers are different for different regions. And putting all this together, we will be able to know what is the best. Actually, I think I wrote it somewhere. So I think because of the time, I know I'm running out, so I'm going to skip the proof. I think I wrote it somewhere. So let me actually, the proof actually was using, surprising, a lot of Calc 2 and Calc 3, polar coordinates, switching and spherical coordinates, and sorry, polar and actually this goes to 3, so spherical as well, and changing derivatives into the rho and theta. So I'm going to skip all this, but say that, is this the one I want to say? Sorry, here, right? Is that we find out that under this theorem that I was just showing you, the optimal kappa should be somewhere like 2 to the negative m over a, which is about 1/4. Actually, it's slightly over 1/4. So 1/4 is 0.25, right? And this is exactly what we predict, or what we observe in the table. This table you have seen earlier. This is also true for other domains. So this is another experiment where we have more than one fracture. As you can see, we have Q1, Q2 is one of them, and Q3, Q4 is another one, right? So here you can this is a triangle where we can compute the alpha, the kappa, which is about 1/8, and that is exactly what we all observe from the table. Okay, so sorry, I'm a bit rushed toward the end, but I think those theorem actually doesn't quite matter as much as the idea. So let me wrap up this really quick. So in this talk, we started some preparations, and then we start asking the first question. The question is, what is the uniform matching method that is optimal? And or is this uniform matching optimal? And we actually learned that the answer is no, just from the 1D case. The 1D case already telling us that is definitely not the optimal case, the optimal matching. And then we ask, well, if I use the gradient matching, what will be the optimal parameter kappa? And then, we know the classic theory does not, the answers we find from our PD books don't really offer us any answer. And then we found through our own work that the optimal kappa should be this number 2 to the negative m over a, where if this solution is in this space. This is offered by 2010 paper. And then therefore for us is, what is the m and what is the a? and then we found it, at least for a few geometric settings like square, like triangles, and all other polygons, and we can answer them. So my final slide is what is next. I think Yifei mentioned that, right? So we were considering the R2 domain with a line fracture. What about this? It's a curve. Actually, some people has done the case of circles, but the general parametric curve, which you learn in multivariable calculus, right? You have a general curve is still not quite well understood. What about in R3, right? So in R3, the singularity, as I mentioned, could be either a line or could be other surfaces. The line, the straight line in R3 was actually done in 2012, but general parametric curves or even more general parametric surfaces or solid in R3 is absolutely unknown, and they're very challenging, both theoretically and numerically. So I think I will stop here. All right, thank you for your attention.
Yeah, thank you for the great talk, Dr. Wan. So any question?
Thank you for the talk.
Yeah, thank
you very much.
Right, absolutely.
It's
Nice
it's a great talk. Actually, you not only prepare our students in real analysis, actually, it's also prepare our students for some concept like a weak derivative in functional analysis. Which is hope our student will learn a lot today. So.
I do have a question. So it looks like this content it has a lot of applications. I'm wondering if you know of more of a specific case where it's used of this.
Oh, absolutely,
fraction.
absolutely. Actually, this goes to the very beginning. Like, where this question about are from? I mean, Laplace equations are static. In other words, there's no time there, right? So if you look at this, right, this is sorry, yeah, like right, it's UXs plus UY. So in other words, often it serves as the steady state of a dynamic system, heat equation or some other equations. So the actual work is to do those to simulate those dynamical system with such fracture of domain, and to understand what is that fracture, how is that a fracture affecting the whole dynamics as time goes. But to answer that question, which is absolutely to my best knowledge, is very little known, is first to know what is going to happen in the long time, right? So this is one of the starting point for us. Is eventually we want to the equation we want to study is Maxwell equation. I mean, especially for me, I partially these days work on Maxwell equations. I want to know what is happening on these domains, and knowing this such steady state would help a lot to understand the time dynamics. Yeah.
Right.
Thank you.
Absolutely.
Thank you. It's a wonderful talk.
Yeah. Thank you.
I have kind of a goofy question.
Absolutely.
So this came up when we're talking about the triangles, because I remember because I know calculus is you have a bunch of qualitative calculus is when you first showed the triangles, right? You have a bunch of tiny things, right? And as you make them smaller, then you get a better approximation. But in normal calculus stuff, normally it's the case that eventually you have the idea that you can get it differentially small, right? It's sort of indefinitely small. And I know that's when and we're not doing it with this thing. And I guess my question is not why aren't you doing that? Because obviously there's a reason you can't. And that's my question is is it the case that you just is it not feasible in terms of it takes too long, or
yeah, so I mean
you just can't make the triangle
yeah, if you think about, okay, let's say okay, so the uniform matching is always choose the midpoint. If I choose kappa to be 1/4, that means I'm choosing this to be at the 1/4, which means that should I do my uniform matching one more time, I will recover all of those graded match, right? And more. So yeah, if you keep doing further and further down your uniform matching, eventually you're gonna squeeze every pixel of your domain into those grid, and you will eventually reach there. But yes, as you said, the issue, of course, is it's not the picture I showed you. toward the end, let me actually be a bit more concrete. This picture was done, let's say when n equals 7. So I'm doing 7 times graded meshing with 0.25, which means if you do uniform, you have to do another 2 to the 7. Okay, 2 to the 7 is what? 128. Okay, this calculation itself was done in Oak Ridge National Laboratory. So it's on a few nodes of the supercomputer there. It took about a day, which means it would took our laptop, like my laptop will be about like a month. And if you do another 2 to the 7, which is 128, that will be another 128 month, right? And then so for one calculation. So
I guess my
that's just the
question
idea,
is
yeah.
not like, I know that like, it's infeasible to do it indefinitely. I guess my question is more so like, is it the case, like, why isn't it the case that like you could do the same, no, and differentiability, like you can invent a formula to approximate like something infinitely small without having to make the infinitely small thing? Like, I guess my question is like, what makes it impossible to do that with the triangles themselves? So like, why is the case that you can't like
Oh,
make a formula to approximate that? Because like, obviously you can't because we have to do this instead. But I guess that's my question.
I you can do that for triangles, right? I mean, the issue is it's really not about the triangle. It's really about the singularity there. Or in particular, it's about the two endpoints of my line. So it's everything, all the trouble, the real troublemaker is always those two endpoints, right? Everything is really about them. We can do various frames on them. I'm not saying this is the only frame you can impose. Actually, there are other approaches to study this. But if you're doing finite element, which is the most adapted method out there, so you think about a lot of machine, a lot of company, a lot of engineers, they already have the established framework to implement finite element. So to know this practically also is the most efficient approach. I'm not trying to say other approach would not work. Actually, we are working on something else to sort of trying to get around this issue. We are. But I think these days people do spend a lot of time understanding finite element because it is so well adapted and it's actually pretty easy to implement.
Okay, so so I guess it's like more feasible instead of trying to like find some like formula that can like approximate like sort of infinitely small things, or like if that even is possible or like feasible. Instead, you can just use like it's just like more simple to use like the finite element.
I would say
Okay.
in my limited experience, often what I encounter is that should something be fairly easy to construct, then it's very
Yeah.
expensive to execute.
Right.
If you want to save time to execute certain things, you often have to come up with a very complicated scheme. That's always the trade-off.
Yeah.
Now, which one will give you the optimal answer? That's what I'm trying to answer in my slides.
Okay. So it's like basically it's like it would be very difficult to create like such a formula in a sense, and it's like and I also like that probably because like I was like thinking as well like if you make such a formula, would it work with like every case compared to like what you're doing right now where like it might be more generally
Right.
accurable?
Actually, I have a perfect example, which is if you search for Runge-Kutta, I don't know if you have run into that. Runge-Kutta is a perfect example for your question where you can see how I always joke with my student how awful it looks. Just to do something very simple to approximate first order derivative, you write 3 lines of formulas.
Right.
But you pay the price there, but what you got is something super stable and super converging, etc. So yeah.
Okay.
Okay.
Okay. Thank you for the good question.
I feel
thanks
like
for the
I was
question.
worried that like asking the question I would like be a bit rude, but like I don't know. I'm grateful to ask it because it was very interesting, I guess, to
Absolutely.
see
Yeah,
like
no, yeah,
the
yeah, no.
shortcomings of like the derivative type stuff, and
Yes.
why we have to do these sorts of approximations.
Yeah, basically, whenever you run into the word differential equations, there's derivative and distinct arrays naturally.
Right.
And then fortunately or say unfortunately, almost all the physical world are ruled by the differential equations. Right? That's how every physical law is written there. That's why this thing matters a lot.
Okay. Yeah, great question.
Thank you so much. Thank you so much.
Yeah. Thank you, Dr. Wan, for this wonderful talk.
Again, thank you very much for the talk.
Absolutely. Yeah. Hope to visit you guys soon. Yeah.
Okay.
All right.
Bye, guys.